So maybe taking off a bit more where Roger left off with free fermions in the Fermi surface. So today I'll very quickly, because I know a lot of you have learned it before already, I'll very quickly go over the non-interacting electron gas, just kind of summarizing the properties. And we will add interactions and do Hartree-Fock theory today, also called mean field theory. Tomorrow we'll talk about the Fermi liquid theory of metals, which is how to think about interactions and explain the properties of metals. And then Wednesday to Friday, we'll switch gears a bit and talk about a special kind of insulator. Which you may have heard of before. It's known as the quantum Hall effect, or the quantum Hall insulators. And so Wednesday, Friday, I hope to introduce it and talk about, on Friday, to talk about some interesting interaction effects, including fractional statistics. That's hopefully where we'll get to by Friday. Okay, so yeah, interrupt me, ask me questions. I don't exactly know how this class works, but as informal as you'd like it to be. So, so let's start here with the free electron gas. So the free electron gas is a pretty good description of a metal, right? So despite the fact that it's free, we just account for Fermi-Dirac statistics of electrons. We basically just treat it with statistical mechanics, ignore interactions, ignore ions, ignore lattice effects, defects, so many things that we ignore. It works really, really well. So it's worth going through quickly and telling you what all you learn by just thinking about the free electron gas before we add interactions. Okay, so the basic Hamiltonian that one starts with for the free electron gas is this guy, which you've seen before. So n here is the number of electrons. To give you a sense, we're talking about something like these many electrons per centimeter cube in typical metal. This would be a density. M here is a mass. M need not have anything to do with the free electronic mass of a bare electron. As you probably learned in last week, you learned the tight binding model last week, is that right? Okay, so if you remember in the tight binding model, you discovered that when you put the free electron gas on a lattice, that you had a dispersion like this. This is familiar, right? Okay, A is the lattice spacing, T is a hopping amplitude, so that when I plotted it, look like this. And if we now imagined expanding this dispersion right by the bottom here, we would get a Hamiltonian that looks a lot like this. Actually, looks exactly like this to leading order, except the mass is h bar square over 2T8, right? So you notice that the free electronic mass just doesn't even appear in here, set by some completely different constants to do with the hopping amplitude, h bar, and the lattice spacing. So this mass here that we would use in this free electron model does not have to have anything to do with this. Tomorrow we'll see that interactions can further affect this mass in very non-trivial ways. Okay, so that's M here. It's just a parameter as far as we're concerned. So, so Roger worked with this Hamiltonian at the end of week 1, and he probably told you that when you put this in a periodic box, you can solve it. You find that the momenta are quantized. Right? These n's are integers. So that the solution is just what you learn in good old quantum mechanics, the first course you take, the solutions are plane waves. The energy is just h bar square k square over 2m. And so then you take these single particle states and you fill them up, right? So then the picture of the ground state, there's two pictures we can draw, and they're both worth keeping in mind. The first is a picture of when we plot this energy versus mod k. It looks like a parabola. And we have some number of electrons, n, right? What we do is we fill all the single particle states up to some energy, up to the point that we have filled n electronic states. If we have spin as well, we would put 2 states per level here, and we'd fill in n over 2 states. Okay, so everyone's seen all this before, right? So this identifies for us 2 important physical quantities. The first is known as the Fermi wave vector. It's the momentum up to which you fill the electrons starting from k is equal to 0. And the second is the Fermi energy, which is the energy up to which you fill the electronic states in the ground state. So all I'm discussing is what does the ground state look like? You take these plane wave states that you solved for here, and you occupy some number of them until momentum mod kf. Okay, so that's one picture. The second picture is to draw in momentum space. So this is, which is x, y, z, kx, ky, and kz. By the way, I've implicitly assumed it. I'm working in 3 dimensions, and I will be for most of this class, but I encourage you to think through what happens in different dimensions. And the physics is, especially in 1 dimension, can be very different. But I'll be working in 3 dimensions. Okay, actually, let me pick a right-handed coordinate system. Okay, so in momentum space, I can plot all the points that I've identified to correspond to the eigenstates of the problem, right? And they'll form so let me just draw in the xy plane. It'll just be a square grid of points, the spacing of which is 2 pi over L in every direction. 2 pi over L in every direction. And then all I'm drawing is I'm drawing a point for every integer here, right? So this gives me I have a grid in 3-dimensional space. And so then that picture in momentum space looks like I occupy all the states up to some radius mod kf. Okay, and this, so you see that when I fill the states up to some radius mod kf, I'm left with a sphere. I have the surface of a sphere. This is actually a surface of a sphere, not a circle, because I'm in 3D. And this is known as the Fermi surface. And will play a very important role in all the low temperature properties of the non-interacting electron gas. Okay, so just to give you some numbers in a typical metal, what are these various quantities? So first we wrote down what the density was. It's 10 to the 22 to 10 to the 23 per centimeter cubed. Now, from this picture, it's easy to work out, and I think you worked this out in the first week, the relationship between mod kf and the density, right? And this follows just from what we said, which is within the radius mod kf, there are some number of states, and the number of states better equal to the number of electrons that you have. So if you put that together, you're going to get this relationship. Between the density of the electrons you have and kf, which is what's the radius of the Fermi surface, okay? So I told you the density is, so we can just plug it in here, and we can figure out what kf is and epsilon f is. So epsilon f is nothing but h bar square kf square over 2m. So in a typical metal, this is anywhere between 1.5 to 15 electron volts, okay? To put this in maybe a more familiar energy scale, you can define a Fermi temperature, which is the Fermi energy divided by the Boltzmann constant. And this converts this energy scale to Kelvin. And then you find out that this is something like 10,000 Kelvin. Okay, so just to pause a moment and take in what that means, what I'm telling you is that the temperature, the energy scale of this Fermi surface, right, up to the energy scale up to which you fill is 10,000 Kelvin, to be compared to room temperature, which is where we usually look at metals and would like to explain its properties, 300 Kelvin. So there's a huge, this temperature is much, much bigger than that, and we'll come back to how that means a Fermi surface is well defined at room temperature. And that's and how this means that metals are one of the best known examples of quantum mechanics at room temperature because of this separation of scales. Okay, so this is worth remembering. A related quantity is the Fermi velocity. It's the average velocity of the particles that are just at this Fermi surface. Okay, so they have momentum h bar kf, momentum divided by mass gives me a velocity. And so when I plug numbers in here, I get something like this. 2 times 10 to the 8th centimeter per second, okay? Again, just to emphasize, this is zero temperature. I'm talking about the ground state of an electron gas, and I've ended up with a velocity for the carriers at the Fermi surface, 2 to the 10 to the 8th centimeter per second. Again, for comparison, if you did your ideal gas calculation at room temperature and computed the average velocity, average velocity, let's just say 3 kBt over m. At room temperature, for a typical gas like nitrogen or something, this is how big it is. So in the Fermi gas at zero temperature, the carriers at the Fermi surface are moving faster than the molecules in this room. Okay, so that's how fast they are. All right, so a few more properties of the non-interacting Fermi gas. One is the density of states. So the density of states is defined as follows. It's d of epsilon. V is volume, and epsilon is energy. So basically what it is a quantity that counts the number of states in the energy window epsilon to epsilon plus d epsilon per unit volume. Okay, so it's a quantity that, roughly speaking, measures how many states do you have of a given energy in this picture. Because we can draw a picture. Each point here tells you what an eigenstate is, but different points have different energies. The density of states measures how many states do you have per unit energy, per unit volume. And it's a useful way to parameterize all the various physical quantities, as we'll see. One kind of obvious property about it is that the integral of the density of states going from zero energy to the Fermi energy is the density. This is pretty clear to everyone, right? This is just saying that if you count up all the states from 0 to epsilon f and divide it by volume, because I said per unit volume, you should get the density that you have. So that's what this tells you. Now, in 3 dimensions, you can work out what the density of states is, and it ends up looking like this. goes as the square root of epsilon. Okay? Should I work this out, or also, again, familiar to everyone? Yes? No? Don't work it out. Nod if you want. If you don't want me to work it out, nod this way. Okay. What's that? Work it out? Okay. So this follows from, you know how you've been doing this K integrals to energy integrals. You did them in week 1. All you're doing is to say that there's one state for every 2 pi over L cubed volume and momentum space. Right? So then what you compare is you say, okay, that means there's one state for this much volume momentum space. Then in a shell of radius mod k, can everyone see this, or do you want me to switch boards? Switch boards? Okay. Oh, wow, okay. I don't know if people always do this, but I'm doing it. Sorry, so we take a sphere in momentum space, kx, ky, kz. Then we say that the number of states in a shell of radius, at radius mod k, of width delta k, is just given by the volume in the shell. Delta k, right? Divided by the volume per state. 2 pi L cubed. Okay, so this is just the number of states that you would have within this shell. From here, using the fact that the energy is related to momentum by this, you say the density of states in an energy shell d epsilon is the number of states within this shell 4 pi mod k square. Delta k is dk, L cubed, times 1 over volume. Yeah? So I'm just putting together 2 facts. One, that I know how to count the number of states in a shell in momentum space. And 2, that if I counted up the states in a shell delta k, using this relation, I can relate it to the number of states in a shell delta dE. Okay, so once you use this, plug this in, cancel dk's in both sides, etc., you're going to get that d of epsilon. Basically, the d of epsilon would go as mod k, which is squared epsilon. Okay, so that's just filling in the factors there. Will tell you how I got the square root one. And so this is a result in 3 dimensions. In 2 dimensions, actually, the density of states is independent of energy. It's flat. So one straight-out application of knowing what the density of states is to calculate something known as the electron compressibility. The electron compressibility is defined as the change in density for a change in the Fermi energy. How does the density change when I change the Fermi energy by a little bit? And by definition, it's just the density of states at the Fermi energy. So you can measure the electron compressibility in an experiment, and basically what information it tells you is how many low energy degrees of freedom do you have. And so this answer tells you have as many low energy degrees of freedom as the number of states on the Fermi surface. Okay? So let me explain that a bit more. Why do I call them the low energy degrees of freedom? To think about that, we need to understand what our excitations look like. Okay, so far, the picture we drew of the Fermi surface was that of the ground state. We said fill fill up to some radius, and that's what the ground state looks like. What do the excitations look like? Well, to get a picture of the excitations, what we do is we take our, I'll just draw I should be drawing everything in 3 space, but I don't know how to draw spheres, so I'll just draw it in 2 space, okay? But you know what I mean. So this is my ground state. All these states are filled. To get an excited state, what I do is I take an electron within the Fermi surface, and I promote it to outside the Fermi surface. Okay, so this is, in doing so, I create a hole within the Fermi surface. This is a hole, and this is a particle. So they go by the name of particle hole excitations, and really you should just think of them as, instead of occupying all the K states within the Fermi surface, you change the occupation number of one of them to a different K mode. Okay, so these are what all the excitations look like. And so now you start to understand why I said the compressibility measures the number of low-lying degrees of freedom. Basically, an excitation, a particle hole excitation here, costs energy above the ground state, given by just what was the momentum of the particle that you put the electron into, minus what was the momentum that it had in the ground state, right? So the hole is the electron, the state that it used to occupy in the ground state. And so you promote an electron which used to have this momentum to this momentum, and in the process you gain, the p square over 2m difference in energy. So you notice that this energy goes to 0 as both these momenta approach the Fermi surface. Okay? This, by the way, I would call that PF also sometimes, the Fermi momentum. So that is to say that if I promote electrons that are just below the Fermi surface, just at the Fermi surface, then I'm paying very little energy cost. It costs very little energy above the ground state. So these are the excitations that one would call low-lying excitations. They cost very little energy. And a quantity like compressibility, by measuring the density of states, is roughly measuring how many low-lying excitations are possible, which they all look like this, just wiggling around the Fermi surface. Okay, so give me 1 second. Should I switch boards? Why not? So the occupation number of the excitations at different temperatures is given by the Fermi-Dirac distribution, which you've seen before. So at 0 temperature, as we saw, so now I define what the NP sigma is the occupation number of the state at momentum p with spin sigma. Okay, so I've suppressed the spin index sigma so far because whatever I do for spin up is the same for spin down in everything that I've done so far. So nothing I've said so far depends on the spin. So at 0 temperature, we saw that I'm plotting this versus energy. We saw that this looked like a step function. That is, we filled all the states up to some energy, which we call the Fermi energy. And now at non-zero temperature, the same picture is given by the Fermi-Dirac distribution. Looks like this. This is 1, this is 0. KBT. So you should think of the Fermi-Dirac distribution as arising within the grand canonical ensemble. So instead of fixing the number of particles as we have before, we now calculate this occupation in the Hamiltonian h minus mu n. N is the number of particles. So instead of just p squared over 2m Hamiltonian, we think about this Hamiltonian. And we allow for the particle number to fluctuate. So we don't fix the number of particles. All we do is fix the density on average. There's an average density. Okay, so the grand canonical ensemble, as opposed to the canonical ensemble, allows for the fluctuations of particle numbers so that the density is only fixed on average. In that ensemble, this is the occupation number on average at temperature T for the different energies. So how do we understand it? Well, at 0 temperatures, the chemical potential, which is this object mu, which fixes the average density. Okay, so mu is set by the Fermi energy. Everything below the Fermi energy is filled. Everything above it is empty. It's a step function. At finite temperatures, just to put it up here, what it looks like. The occupation number is given by this function, which you've seen before, the Fermi-Dirac distribution. And pictorially, basically what it does is it smears out the step here on the scale given by kBt, which is inverse of beta, the parameter here. Okay, so now we can use what we knew about Tf and T to understand why our Fermi gas is a very quantum mechanical object. So remember what we said? We said that the epsilon f, the Fermi energy, corresponds to a Fermi temperature, which was like 10,000 Kelvin. Right? So that's telling you that in this plot, this scale here, which sets the step, is at 10,000 Kelvin. At room temperature, this step is smeared out only on the scale of something like 300 Kelvin. Right? So this is the sense in which we say the Fermi surface is well defined at room temperature. Even at room, if I plotted this to scale, somehow even at room temperature, this looks very, very narrow. This is basically set by the Fermi energy, and this smear is very small. It's kBt. Okay, so that's why we say the Fermi surface is well defined at room temperature, and that's why when you will do this in the homework today as well, you will calculate the specific heat of the Fermi gas by doing the Sommerfeld expansion and so on. So I'm not going to go into it. The answer that you'll get, so the specific heat, just to define it, is defined as follows. E is the total energy of the gas, T is temperature, V volume, and number. Specific heat measures, roughly speaking, it's a specific heat capacity of the gas. How much does the energy increase on changing the temperature by a little bit? And it's again a measure of how many excitations the system creates when you change the temperature a little bit that carry energy. Okay, so that's a specific heat. So this is an object you've encountered before in classical mechanics, and probably remember the answer, which is for an ideal gas, it's 3/2 kb times the density n. Right? So it's independent of temperature. No matter what the temperature of the ideal gas is, the specific heat is the same. Now, when you do the calculation for the Fermi gas, you're actually going to find this answer today. Okay, so which is the most important fact being that it's proportional to temperature. So that if I plotted this CV versus temperature, at temperatures much above the Fermi surface, Fermi temperature, this result holds true. Basically, what it's telling you is that if you go to really high temperatures, you can't tell that it's a fermion or boson or whatever. The classical Boltzmann calculation is good enough, the ideal gas calculation becomes exact, and you get that answer at really high temperatures. However, at low temperatures, low compared to the Fermi temperature, which is room temperature, we find that the result is significantly modified. It's much smaller than what you'd predict from the classical calculation, and it's given by this. And so I just want to emphasize this is one of the big tests of quantum mechanics in a condensed matter system that, which it's like a success of quantum theory in condensed matter, that a complicated material like a metal obeys this and not that, and you can just explain it with simple Fermi-Dirac statistics at room temperature. Okay, so that's the speedy, non-interacting gas overview. The key points to take away is that it works really well. The only thing going beyond normal ideal gas is that we put in the Fermi-Dirac statistics. This gives us the idea of the Fermi surface, which is responsible for all the physical properties of the metal at room temperature, all the thermodynamic properties of the metal at room temperature. Okay, so now let's put in some interactions and ask, how is this picture modified? Okay. Any questions so far? No? Okay. Okay, so the Hamiltonian that we really want to understand has two parts to it. One is the part that we've been talking about. I'll explain all these symbols in just a moment. Okay. Is everyone comfortable with second quantized notation? Right? Okay. So that's what I've switched to here now. So these C's that I've written down are fermion, creation, and annihilation operators. So so C alpha K here is the Fourier transform of this guy, C alpha J minus I. Sum to J. So alpha here is the spin index, K is momentum. Okay, so to connect back to your tight binding model that you're thinking about, think of this fermion annihilation operator, or the creation one, as creating or annihilating an electron in some particular orbital. So remember you had this picture. So these are the ions. We imagine some electronic orbitals localized around these ions. And then the tight binding problem that you solved for was to ask about the question of what about electrons hopping between these localized orbitals on the different ions, right? That was the tight binding model you solved. So think of this C alpha J not as creating an electron at position J, but at creating an electron in the orbital kind of localized around position J, okay? And so that T was a hopping amplitude, and this was a problem that you solved before. It's not very important for what we will be talking about, so if you find that confusing, you can think of this as just creating it at position J. But in a realistic model, we're imagining some smeared out orbitals. Okay, so as usual, these fermionic operators satisfy, and they anti-commute with one another instead of commuting one another. And to be simple, we're just going to imagine that there is only one orbital per site for now, so that to connect with the tight binding problem, there would have been exactly one band who's in the Brillouin zone, whose dispersion would have been something like this. And so that here is psi of k. Psi of k for me is the dispersion of a single band in the Brillouin zone, and C alpha k represent the orbitals in momentum space. Okay, so this part here you should just think of as a tight binding problem that you solved before. We've accounted, going beyond the free electron approximation, we've accounted for the ions, and we've put in the periodicity, all the stuff you learned about block waves. All that is in here. The new part that we want to think about now is this here. So that's the kinetic energy, if you wish. This here is the potential energy. And what is this term? This term is an interaction between the density at site I and the density at site j. Okay? N hat alpha of I measures, as by definition here, just tells you what the number of fermions is with spin alpha and at site I. And so this interaction here is a density-density interaction. So in maybe a familiar one is the Coulomb interaction, in which case this would look like this. This is Coulomb. But another useful interaction that doesn't have some of the problems associated with the long-range behavior of Coulomb is a short-range repulsive interaction, which looks like this. So only when the fermions are right on top of one another, only when they're exactly on the same site, is there a strong repulsion. Otherwise, they don't see one another. That's called short range. Okay, so this is a repulsive interaction between fermions, can be of the Coulomb form, can have a more short-range form. And we're interested in understanding how this piece of the Hamiltonian affects our solutions for this. How does it change the properties that we've discussed, which was just of this? Okay, so the problem is clear, right? This is the interaction term, that's the free term, and we want to know how does this affect that. And just to be super clear, this part, as you can see, is quartic in the fermion term. So this is quadratic, involve two operators. If I wrote this out, because each n alpha has 2, this is a 4 fermion term. Right? So this is an interaction term. And in general, we don't know how to solve it. So what we're going to discuss today is an approximate way to start to solve this Hamiltonian. And it's called the Hartree-Fock approximation. Okay, so I'm going to do a bunch of the algebra on the board, but before I do it, let me lay out what the plan is, what I want to get to, how I'm going to do it, and then I'll go through all the algebra on the board. Okay, so the Hartree-Fock approximation says, well, we don't know how to solve a quartic, a generic Hamiltonian like that. It's just too hard. So let's start with a guess. The guess being that maybe the eigenstates that we found in the free problem, the free non-interacting problem, are a good starting point, good variational starting point for this more complicated Hamiltonian. Okay, so what we're going to do is we're going to take psi 0. Psi 0 is an eigenstate of only the free part of the Hamiltonian, so which I'm going to call H0. So it's up there, and it's this bit. Did I swap? So psi 0 is an eigenstate of this free Hamiltonian. We know that we can specify every eigenstate of this Hamiltonian by just the occupation numbers of momentum k and its spin alpha. So there's a set of these occupation numbers for each spin and each k that specifies every single eigenstate of this problem. So the ground state was, for example, and k alpha is 1 if k was less than kf and 0 otherwise, right? This was the ground state that we talked about. But in general, any eigenstate of this Hamiltonian can be specified by just telling you what every single occupation number is for all the k-modes. This is the ground state. And so we're going to think, we're going to guess that an eigenstate of H0 specified by these occupation numbers is a good variational state. What does that mean? That means what we will do is we will calculate this quantity. H is a full Hamiltonian, having the interaction part too, right? So we guess this is a good ground state. We compute the average energy within this ground state, within this state, okay? And I want to emphasize, we're not saying that it's an eigenstate. This is not the claim. We're not trying to find the eigenstates. We're just doing a variational calculation. So we compute this object. This is the average energy in the state. And once we do this, we minimize it. Yes?
When you say that we calculate the average energy with psi 0 and then minimize it, if psi 0 is an eigenstate of the free Hamiltonian, you have no parameter to minimize with respect to, right?
I have these. These are my parameters.
So you're okay.
So I will choose those occupations that will minimize this. But that's the only parameter I have, indeed. Any other questions? And as in the eigenstates, these have to be always 0 or 1, just like before. Right? And so that's what I'm going to do. Okay. So that's all we're going to do. And this is, first pass at trying to solve this non-interacting problem. Let's just guess and minimize an energy within some guess state and see how well we do. Okay, so now I'm going into the algebra. So I'll try to break it up in some way. So to do it, let's first rewrite our interaction in momentum space. So H naught was this free piece. H interaction was the 4 fermion term we wrote above. And in momentum space, it looks like this. Okay, so all I've done is taken something that was written down in real space, inserted the Fourier transform of all 4 momentum fermion operators, and I arrive at this form. Okay, so I just want to point out 1 or 2 things about this form. First, notice that in here now, instead of having the potential in real space, I have its Fourier transform. So to connect to the 2 examples that we had, in the short range case, the repulsive interaction looks like this, V, where V is a function of I minus j, and it's non-zero only if I is equal to j. Right? That was the short range case. So Fourier transform of this, it's a Fourier transform of a delta function. You'll just get something uniform in Q space. the other example was Coulomb. For Coulomb in repulsion, we said V of I minus j falls off as 1 over mod I minus j, 1 over R potential. And the Fourier transform is VQ is 1 over k squared, right? Which is the familiar Fourier transform of the 1 over R potential. So that's what's going in here, the Fourier transform of the potential. These are now creation and annihilation operators in momentum space. And the other important point to notice is that the total momentum of all these 4 operators adds up to 0. Yeah. Sorry?
Is there an issue of normal ordering of the operators?
So you can do this with normal ordered operators. Just think of this. This is my Hamiltonian, right? And there's no issue with normal ordering because, we'll have pieces that come from anti-commutation relations because of not normal ordering these, but there'll just be some constant pieces. We'll keep track of them.
But the thing is, I see this formula, and it's usually written with the creation operators all to the left. So if you want to make it all to the left in this case, you'll pick up a minus sign. And so your interaction term will be repulsive instead of, attractive instead of repulsive.
So hold that thought. We will get a part of the interaction term that's negative, and we'll interpret it coming from that.
But I'm saying that the overall...
No, the overall, overall, this term is a repulsive term, right? You can, if you subtract out some constant pieces from the repulsion, there is a piece that's attractive coming from swapping these, right? But so I don't want you to take the field theory point of view that everything should be normal ordered. I'm trying to motivate this Hamiltonian coming from physically, what should you write down? Okay, physically, I know if I have charge here and I have charge there, they interact by Coulomb interaction, right? Having charge here is having a density of charge here, and so the operator that I should write down in the Hamiltonian is not normal ordered, and so I'm not going to normal order it just because. Okay, so I just want to say that it's physical that I write this down, not the other one now. And I'll tell you again where your issue of normal ordering will come in. Any other questions? Okay. Okay, so we have this now in momentum space. Oh, wow, I have no points. And we're now going to use Wick's theorem to decompose. So now we want to calculate this, right? This is step 1. And this has 2 pieces, H0 sandwiched between psi 0 and H int sandwiched between psi 0. To calculate H int sandwiched between psi 0, we're going to use a Wick's theorem. Okay, so we want to calculate this bit first. And to do this, we need to know what something like this looks like. Right. This is clearly the only determinant that we need to know, and then we have to sum things up. So you've all seen Wick's theorem in the context, I think, of field theory. This is yeah.
Sorry, I just have a question about the Hamiltonian. Could you explain why we have a alpha k minus q and a beta k prime plus q? I know it comes from the Fourier transform, but...
Do you want me to do the Fourier transform?
Well,
or?
I don't know, because I guess I would expect there to be a q in both terms.
Well, you could equivalently rewrite this as k prime. If you've seen this, and that's more familiar. But that's literally rearranging, they're all dummy variables, right? So I can just, yeah. So it's the same as that. Okay. So you've all seen Wick's theorem, I know, because you're doing QFT2, which is, you've definitely seen Wick's theorem by now in the context of field theory and path integrals, right? So this is the second quantized version of that same concept, which is that a 4-fermion operator evaluated within a state which is a Slater determinant state, right? So psi 0, if I wrote it out in second quantized notation, just looks like all occupied case acting on the vacuum. This is familiar? I just write occupied here, which is to say whichever states are occupied, you insert that creation operator in here. So that's what psi 0 looks like, right? So within any such state which has this form, there is a Wick's theorem in the same way that you've learned before in field theory, which is that these 4 fermion terms decompose into products of expectation values of 2, right? So you do sum of all pairs, as you've done before. So if I did that, I'd get 3 terms. And I'm not going to write down the psi 0 explicitly when I write down expectation values, but it's implied. So the first term is with this pairing. See, alpha. The second term is with this pairing. And the last one is with the third pairing. So the way I've ordered the operators, I don't pick up a minus sign. Okay, so yeah, I mean, you have to just check that this is true. Yeah, and not all my operators are normal ordered again, even within these, which might again be another place that minus signs come from later. Okay, so I have 3 terms coming from 3 different pairings because there is a Wick's theorem satisfied for expectation values within psi 0. So straight off the bat, I can say that this is 0. Okay, so why is this 0? This is 0 because in both these terms, you notice that the occupation number of so these are, remember, they're acting on a state psi 0. Looks something like that. And the occupation, it changes the occupation number by 2, right? This creates 2 more fermions. This destroys 2 fermions. And so when I sandwich it back with the same state, because the occupation number has changed, the overlap will be 0. Right? Is this part clear to everyone? The only way I can get non-zero overlaps when I sandwich between a state with fixed occupation number is if I don't change the occupation number. So this is okay, has 1 dagger, 1 no dagger, 1 dagger, 1 no. Those 2 terms are okay. So straight away I know that I don't have to think about these 2 terms. Right? So now I have 2 terms left. So I'm going to call this one 1, that one 2. And now I'm going to go term by term and write out the contributions to the total energy. Okay. So first is, let me just write out what the contribution due to the non-interacting piece is, H0. Remember, this is just a term in H int. And so this is easy. It just looks like energy times occupation number summed over K alpha. Okay? And K alpha, again, are my parameters that that tell me what psi 0 is. They're the occupation numbers in psi 0. Okay, so this is easy. This is just what we saw the beginning of the class. If psi k, the dispersion had some form like this, then to minimize this part of the energy, I would do exactly what I did in the beginning of class. I would just fill the states up to some kf, and I would put all the spin downs and the spin ups, both spin down and up, in the bottom of this band, right? And that's what we did. This is how we define a Fermi surface, et cetera, et cetera. So that part we know. Let's now look at term 1. This is known as the Hartree term. And we put it back in the sum for h int, right? So we have some 1 over 2 in sight. Okay, so I just have rewritten this term in here. This is what I call term 1. It's called the Hartree term. So let's look at these two expectation values here. So this could be non-zero within the state psi 0 only if k is equal to k minus q. Does everyone see that? Again, by the fact that if I destroy a fermion at a different momentum and create it somewhere else, I'm going to have 0 overlap with the state I started with. Right, so you see this forces k to be k minus q. This forces k prime to be k prime plus q, which is the same thing as saying it forces q to be 0. Okay, so the only non-zero part to that sum comes from, is this basically, sum over O. VQ, I've set Q is equal to 0, and K alpha, and K prime, K prime. Okay. And now you notice that sum over all K alpha, summed over all K and alpha of NK alpha, this is just the total number of particles. Right? Remember, NK alpha was the occupation number of momentum k and spin alpha. So if you sum all the occupation numbers up, you're going to get the total number of particles. Similarly for this. So now we're left, this term then just looks like V0, which is the 0 Fourier component of, yeah?
What happens when you consider Coulomb interaction where you V0?
Diverges. Yeah, I'll come to that. Just 1 moment. So I jumped the gun a bit, but let me just say that. V0 for the short-range case, because we plotted the Fourier transform, is just U0. For Coulomb, as was just pointed out, VQ goes as 1 over Q squared, and that formally diverges at Q is equal to 0. So two points there. First is the really long wavelength divergence of Q is coming from the fact that at very long length scales in the Coulomb interaction, I've assumed that I have a true power law. So this ignores the fact that in usual gases you have screening. And in the screening, effectively what it does is it makes this Yukawa in sort of a true Coulomb interaction. So that will cut this off, first off. Second, which maybe addresses the normal ordering point brought up before, is that if to do this, the other piece of the energy that I've ignored here, which will also be divergent, is the interaction between the electrons and the background ions. Because I know that I have a net neutral medium. It's not like I just have charged particles floating around in the metal, right? So once I put in that neutralizing background, I would actually cancel this divergent piece of the energy. Right? And so normal ordering, what it does is it automatically cancels out these divergent pieces. It's another way to think about it. Okay, so, but bottom line is this Hartree term, notice it's independent, completely independent of exactly what the values of nk alpha are in the state that I picked. So in the variational scheme of things, this is not going to help, this term is not going to help me differentiate between the different possible states, guess states that psi 0. Okay, so that was term 1. Let's do the term 2, which is known as the Fock term. And so just to write it out, okay. So once again, for these expectation values to be non-zero, we would need alpha to be equal to beta and k to equals k prime plus q, right? K minus q. For the same reasons that we just went through there. If you don't create and destroy the electron at the same k and spin, you would have no overlap with the original ground state. And so this a delta function would enforce these two constraints so that when we put them in, this becomes summed over alpha. Let me just try to see alpha k dagger, C alpha k prime. Okay? Where all I've done is enforce these constraints, and so that's removed two sums for me. The sum over q is gone, and the sum over beta is gone. Okay? Okay, so this we now identify exactly to be the occupation number in, I think I called it k alpha, in momentum k and spin alpha. This is, we use the anti-commutation relationship, and we get that this is actually 1 minus n k prime alpha. Okay, so we plug these two in. We see that we have two terms, one coming from multiplying this out with the 1 and the other from the product. So all right, so clear, pretty clear. There was a constant term that came out, which once again, just by 1 or 2 steps of algebra, we see that it's independent of the occupation numbers nk alpha. It depends only on the value of the potential in real space on site. Once again, this is something that's divergent in the Coulomb case, but would be cut off in the case where we have a lattice. There's natural cutoff, so this isn't actually divergent. For the short range case, v of 0 is just u, whatever it is, u0. So this is some constant piece. And here is the piece that we actually want. Okay, so important sign, it's negative. This negative sign came from the anti-commutation relationship. So it's brought up before. So what is this term? Let's understand what this term is telling us. One, the negative sign actually says that it's an attractive term. Okay, but an attractive term between what? It says that there's an attractive interaction between the density of at k and k prime, but with the same spin index. So it's an attractive interaction between spins which are aligned, parallel spins. Okay, so, what is the physics of this term? Where is it coming from? Well, it's actually coming from Pauli exclusion principle. We know that Pauli exclusion principle dislikes having, or not dislikes, it disallows electrons with the same state, two electrons with the same state. So you cannot have two electrons with the same spin sitting at the same momentum or sitting at the same point in real space, right? So automatically, because of that, it costs lesser energy when you put in a repulsion term between aligned spins than between anti-aligned spins, because anti-aligned spins, fermions with anti-aligned spins, there's no problem with them just being in the same point in space. Not Pauli exclusion doesn't care, but the repulsion term is very unhappy, costs a lot of energy. On the other hand, aligned fermions, because the Pauli exclusion principle keeps them apart, automatically the repulsion term gives a lesser cost to this configuration as compared to that. Okay, so this minus sign you should think of as a relative energy cost between this configuration and this. It says that this has lower energy than that because Pauli exclusion keeps the spins apart naturally. And you've seen this before in chemistry. This is where Hund's rule comes from in an atom. So the reason you follow, when you fill electrons in orbitals, you always fill, and different orbitals have the same energy, you always put in electrons with spin polarized in the different orbitals. And that's exactly this cost. It's because the energy is lowered if the spins are aligned, okay? And so that's the physics of the Fock term, and I want to emphasize the relative attraction. It's not an overall attraction between electrons. And this is the only piece that we managed to find which actually cares about the occupations of occupation n k alpha. So this is what we're going to minimize. We're going to minimize this term now when we minimize the energy for our variational state. Okay, so we put everything together, and we write down what the total energy is, which was just this guy. And we can write it in this compact form, basically. Okay, so I've just put together all the different pieces that we discussed. Kinetic energy, I've brought in the chemical potential here, which I just H minus mu n, right? So that's a part of the Hamiltonian. This bit came from the Fock term. This was the Hartree term, and this was the negative term from the Fock term. And so now to minimize the energy, what we do is we determine the change in energy when we change the occupations by a little bit. So I'm going to actually write it this way. basically this term here. Yeah.
What does it mean here to make a variation of the and k alphas? They're just 0 and 1.
Well, so what we're asking is, well, the d and k alphas are 0 or 1, basically. So we're asking how much does the energy change if you change the nks. If they're 0, you make them 1. If they're 1, you make them 0. So yeah, we're not doing continuous derivatives or anything like that. We just want to, this is an easy way for us to find out what the minimum values of nks are, where we will put the constraint on that all the nks are integers. Okay. So this term here is just basically this, and I've just collected terms, all the constant terms into some effective chemical potential, some mu prime that I've defined. And so you basically see, and now let me call this psi k star. So you basically see the condition for this to have minimum energy within this variational class is that whenever psi k star is negative, then we occupy such states, and whenever it's positive, we leave them empty. And this is psi 0 such that okay. And so how do I see this? Well, whenever this is negative, if it's occupied, then delta n is negative, right? It goes from 1 to 0. And so this product is positive. Whenever this is positive and it's unoccupied in the ground state, the change in delta n will be positive. So this product is positive. Basically, I require that the change in delta E, for the psi 0 to be a true minimum, the change in energy for any change in occupation better be positive. That's what I'm asking. So if it has to be positive, I want every term in this sum to be positive, and it will be positive if I make this choice for psi 0. Okay? So we've done the first part of our task. We've identified, we've got the condition for the guess state that minimizes the energy of our full-blown interacting Hamiltonian. Okay, so let's pause for a moment and ask what this new ground state looks like. Yeah.
So the idea is you choose the eigenstate of the free Hamiltonian and then project the Hamiltonian into the subspace, right? I mean, into the ground state of the free Hamiltonian. Why is this a good approximation to the ground state of the full Hamiltonian?
I will justify in a minute. Yeah. But at the moment, at the moment, you just think of it variationally, right? You know that you can always guess a state, and an energy that you calculate from it will always be an upper bound to the true ground state energy. So think of this as an upper bound to the true ground state energy at the moment. Oh no, I'm out of build space. Okay. So we have our guess state. Let's ask what it looks like. What was the answer that we found? Because the psi k star seems like a complicated function. Exactly what does it mean to fill it when it's negative, etc. Okay, so let's do both the short range case and the Coulomb case really quickly. So again, the short range case meant it was only repulsion on site. Coulomb was this. And so when we plug in for the formula here with this thing, we actually find that this is rho 0, where rho 0 is the density. Okay, so this sigma k alpha that I defined there coming from the Fock term, negative, good. And it turns out that it's actually independent of the occupations in size 0 for the short range case, and again ends up being some constant that depends only on the density. This is not going to be the case for Coulomb, so it's just a special case for the short range. Okay, so anyway, let's take it at face value and ask, what does this mean? It means that if without interactions, I had a energy spectrum that looked like this. Now with interactions, psi k star defined there, the energy for every k is lowered by this much. So it's just a constant shift, okay? Everyone sees that? So all that's happened is, so that I would fill it till here before, now I fill it till somewhere, and independent of the value of momentum, all that's happened is that in the ground state, all the energies have shifted by some constant amount. And so I just fill this new dispersion up to, n for n electrons, and that's my new ground state. And you see that it will have lower energy than this just because everybody's energy has gone down by a little bit. Okay? So that's the short range case. What about Coulomb? For Coulomb, sigma, so you see that we are stuck with a little bit of a problem. To get to figure out what psi 0 looks like, to use this condition, we need to know what psi k star is. But to figure out what psi k star is, we need to know what the occupations are, right? So you see that we're stuck with a self-consistent problem to solve in general, and we may not know how to do it. So here what I'm going to do for the Coulomb case, in anticipation of when the result is actually valid, I'm going to guess the occupations in psi 0, okay? Although I should be solving it self-consistently. And I'm going to guess the answer, basically, which is that the occupations are exactly the same as in the free ground state, the non-interacting ground state. Okay, and again, just to emphasize, this is what I should self-consistently solve for. It's a complicated set of equations that I don't know how to do it. So, imagine that this is some iterative procedure. I'll guess, get the answer, put in a new guess from the answer, etc. So this is my starting guess, which is just the ground state occupations. So now I can use this and actually calculate sigma k alpha. Okay, this is the formula that I have up there. Only difference being I've taken the continuum limit, replaced the sum times 1 over volume with the integral. And then I put in, and so then I put in my guess that NQ alpha looks like this, so which means that what I do is I only take the integral up to kf. Times this stuff, right? Times 4 pi square. Okay, so now you can just plug this integral into Mathematica after a few steps of simplification, right? So I'm not going to do it on the board. You can do the integral, write this thing out as q squared dq, do the cos theta integral, etc., and you get this answer. Okay, So I have an answer now for this quantity, which depends on K explicitly. Yeah.
When you wrote the Fermi momentum, you make reference to the Fermi momentum on the free theory, right?
Yeah.
Okay.
Yeah. That's right. And which has the same relationship with the density as I wrote down in the beginning of the class. So density fixes it. Okay. So for the Coulomb case, we noticed that we explicitly have K dependence. The answer, the energy actually cares about what K is, because I've defined a Y, which is dimensionless, that cares about K. Right? So to see what this quantity is, let me plot it for you. And remember, this quantity is the shift in the energy between psi K and psi K star, taking away the chemical potential, right? So psi K star is psi K plus sigma K alpha. So knowing what this shift is tells us what our new dispersion is that we're going to fill. And so this thing looks like this. This is K. Square over pi. Okay, so there's some constant dependent on Kf, and it's something that is always negative. The lower K modes are their energies shifted more, brought down more than the higher K ones, right? And importantly, this tells you something about my guess, right? So if my guess were true, I would have found that I wanted to fill the states exactly up to the same Kf as in the non-interacting one. Here you notice that's not true because the energy is actually lowered. So I actually would like to fill more states if I kept the same chemical potential. Right? So that tells you, that's how you would iterate this procedure. Okay, you guess it, you got some new dispersion, you fill this new dispersion as if this was the right answer, plug that back into this guy, get a new dispersion, and so on. Okay, so that's how you would get the actual right answer. But it still told us something important. It told us everybody's energy is lowered a little bit so that even at the Fermi momentum, you would like to fill more states than in the non-interacting gas for the same chemical potential. So now, okay, we have 5 more minutes. I'll say it really quickly. So 2 final points about what we learned doing all this. One thing we actually learned is that there is an effective theory for my interacting problem within this approximation. The effective theory is not only for the ground state, but also for the excited states, and looks like this. It has the dispersion modified by that quantity from the Fock term, but otherwise looks much like my non-interacting problem. Okay, so this is always what Hartree-Fock, or another word for it is mean field theory. This is always what it gives you. It takes a horrible interacting problem, works within the variational class of non-interacting states, and gives you an effective non-interacting Hamiltonian in the end for both the ground state and the excited states. Only difference is being in it modifies the dispersion. Okay, so the interactions have only come into this guy here. That's where you built them in. And so in particular, this means that there is a one-to-one correspondence between the states of the free problem and the states of the interacting problem. It means that the energy of a particle hole excitation that we discussed is now modified to psi star p minus psi star h, p and h being the momenta of the particle in the hole. And one important point, the energy of multiple quasi-particles, right, or not quasi-particles, multiple particles or multiple hole excitations depends on the presence of all the other fermions in the problem because of this term. Basically, this contribution to the energy cares about what all the other fermions are doing, right? So in the energy for state K knows about what all the other Qs are doing. So because of that, if you created, say, 2 particles in 2 holes, it's not going to be just, add this up twice. The answer is going to be different because the presence of fermions affects every other fermion. So that's important to remember. It makes the problem nonlinear. Okay, so finally, coming to why should this work? When, or maybe more constructively, when should we believe this result? When should we say we've actually solved the problem? Okay, so, right, I need a new board. To see when we should believe our answer, let's use our own answer to tell us when we should believe it. So I'll rewrite the result I got for the Coulomb case here for psi k star. So psi k star times f of y, where this is a function of y, so I'm not going to write that down. Okay, so if I use the fact that the Fermi energy is defined like this, and I set the new chemical potential to be equal to the Fermi energy, then I get okay, sorry. So all this y here, just so it's not, it's just the dimensionless k over kf. Okay. So all that's been said is that the modified dispersion, this part is the usual dispersion. It's just because I pulled out kf squared over 2m. This is just k over kf squared over 2m minus mu. Mu is equal to the Fermi energy, so it's minus 1. And this bit here is the only thing due to the interaction. Okay, so you would expect that somehow our guess that the non-interacting states are good enough would be a good guess if this is small compared to this, right? Because we know that our answer was correct in this limit. Now we perturbed away from it by adding interactions. So we would expect our answer to be right only if this is somehow small compared to this. Okay, so there's a physical meaning for what this small means, actually this small. And that comes out by thinking about this quantity called Rs. So Rs is the dimensionless ratio of the potential energy to the kinetic energy. Potential energy being an interaction term, kinetic energy being the kinetic term, right? So let the interparticle spacing be A. Okay, so this quantity A is, roughly speaking, just proportional to the density to power 1/3. Everyone sees that, right? The density sets, if I take the 1/3 power of it, I'll get an inverse length. And if I take the inverse of that, I'll get a length scale. That's roughly speaking the interparticle distance. So this interparticle distance, I can now ask what is the potential energy and the kinetic energy at this interparticle distance. So very crudely, potential energy is E square over distance. Kinetic energy is h bar square k square. I know k looks like 2 pi over A over 2m, right? Very roughly. And so once I do this up to constants, I get that this looks like A over A naught, where A naught is the Bohr magneton. Yes? Oh, Bohr radius, sorry, yeah. Yeah, Bohr radius, sorry. Yeah, so this is a dimensionless ratio of length scales. A naught, maybe it's not so surprising the Bohr radius plays a role in, because we know that we solve the one particle problem of, with the one electron with this potential energy and this kinetic energy, that's the hydrogen atom, and we find the Bohr radius as the scale for the size of the atom, right? So that's the natural length scale that appears here. The only other scale is in the problem, because we don't have one electron, but we have many electrons, is the spacing between the electrons. So this is this ratio RS. Why bring it up? Because if you rewrote this, you would actually find that this term is proportional to RS. Okay, so the constant piece, which we said should be small for our analysis to make any sense, is proportional to RS. So we now can physically argue when and why our analysis makes sense. By drawing a phase diagram. Okay, so this line is increasing RS. RS is 0 is when, because it's potential by kinetic, it means potential is 0. That's the non-interacting gas. Here's my free Fermi gas. And that's where we started our class with, at RS is equal to 0. We now argued that our Hartree-Fock analysis, this whole correction to the energy, etc., could only make any sense if the correction is small compared to the original energy, right? And the smallness was set by RS. So now we can draw, okay, so somewhere around here, very close to 0, maybe here our Hartree-Fock analysis could be useful. Okay, so that's still really close to 0, and it makes sense to us because 0 is the free Fermi gas. Okay, so we're near the right limit. Also, to point, when RS is really, really small, it means A is much, much less than A0. Interparticle spacing is much, much less than the Bohr radius. This is actually the very dense limit of the gas. Okay, it's actually a little bit counterintuitive. It's when the gas is very, very dense is the free approximation valid. Okay, that's what this is telling you. The opposite limit, when RS is very, very big, it behaves basically classically. You can use the potential energy dominates over the kinetic energy. You know, and if you forget the kinetic energy entirely, you know you have a problem of electrostatics. And if your problem of electrostatics, charges repel, they just form a crystal where they try to just stay away from each other as much as they can. So this is the limit of actually a crystal. It no longer behaves like a gas, not a metal. It's actually a crystal. And so everywhere in between, there's this large part in between that we've not described in this class, okay? But it turns out experimentally, even up to RS going up to 10, experimentally you see metallic behavior. And not just metallic behavior, you see behavior very much reminiscent of the free gas, okay? By which I mean this specific heat that we introduced at the beginning of a class is proportional to temperature, just like the free gas. This compressibility that we introduced is a constant, independent of temperature, etc. So our task in the next class is to ask ourselves, how can we reconcile this? Where, when the interactions are so strong that the free limit has no business working, why do we experimentally see the same behavior as if this was a non-interacting gas? That's what we're going to talk about next time with the Fermi liquid theory. Thanks.